Hello everyone, I'm Zheng Bangchen. Now I present our work for verifying message passing interface programs. This is joint work with Hen Biaoyu, Xian Jinfu, Ji Wang, Chun Huang, Wei Dong in my university, and Zheng Dongsu from ETH, and Jun Sun from Singapore Management University. So our concern is the parallel programs on high-performance computing. MPI is the current de facto standard for developing the applications in HPC. MPI provides a standard that implements the style of message passing-based parallel programming. MPI applications are non-deterministic. The developers can use blocking and non-blocking communication primitives in MPI programs. And MPI programs are usually for scientific computing. Inside the programs, data and control are intensive. It's well known that MPI programs are hard to develop and maintain. The verification of MPI programs is pretty challenging. On the one side, the non-determinism challenges the verification. Both the inputs and the schedules of the programs may cause non-determinism. For example, for this program, when the input X of process P1 is equal to A, and the wildcard receives the message from P2, the dialog happens. Because the last receive cannot receive message from P2 anymore, so P1 cannot terminate. To detect this deadlock, the verification should cover both input and schedule. There are some existing approaches for MPI verification. Existing approaches either do not support input-related verification or fail to support the verification of non-blocking MPI programs. Our approach, called MPSV, is an automatic verification tool and covers the program input and supports the verification of non-blocking MPI programs. Another challenge is the explosion of the program state space. The explosion is caused by parallel executions, non-deterministic communications, and branch statements in the program. Because of this, the exponential increasing of program passes is more serious for MPI programs. To handle the first challenge, we use symbolic execution for input coverage, which is pretty natural. To cover the different schedules, we use a blocking-driven style for getting the matchings of wildcard receives. The basic idea is to record the communications between processes first until all the processes are blocked. Then we do the real matchings and unblock the processes. In this way, we try to get all the matchings of wildcard receive operations. Besides, during calculating message matchings, we preserve the happens before requirements in MPI standard. To handle the second challenge, we leverage the idea of partial order reduction to avoid full interleavings. Besides, we use a model checking based boosting to improve the efficiency further. Here is the basic framework of MPI-SV. The inputs are an MPI program, the number of processes, and a verification property, such as dialog freedom. Now MPSV supports the properties in linear temporal logic. Then we use the blocking-driven symbolic execution method for analyzing the program under the input number of processes. When the symbolic executor exploring the passes, if there's a violation of the verification property along the path, MPSV terminates and reports the counterexample as a test case. Otherwise, when a path terminates normally, a CSP model will be generated. This model encodes the equivalent passes of the current path. All the passes in the model have the same path condition, but have different matchings of wildcard operations. Then we feed the model and the property into a CSP model checker to verify whether the path model satisfies the property. Because our modeling is sound and complete, if the model checker reports that a violation exists for the path model, MPSV finds a real violation and generates a counterexample. Otherwise, if the model checking reports that the path model satisfies the property, we can prune all the equivalent passes in symbolic execution to boost the verification. More details of CSP modeling can be referred to our paper. So from a high-level view, MPSV combines symbolic execution and model checking in a synergy manner. Symbolic execution is used to automatically extract the path models from the MPI program. Then the models are verified by model checking. The results of model checking can be used to boost verification in both counterexample finding and path pruning. What's more important, in this way, model checking can enlarge the scope of verifiable properties. Pure symbolic execution can only verify reachability properties. MPSV can verify LTR properties. We have implemented MPSV and carried out the experiments on real-world MPI programs. Here is the main result. MPSV is more efficient and effective than pure symbolic execution. For 111 verification tasks, MPSV can complete 100 tasks. Pure symbolic execution can complete 16.1. For deadlock cases, MPSV achieves at least 5 times speed up. For low deadlock cases, MPSV achieves lightning speed ups. Here is the progress distribution of the verification tasks. The x-axis is the verification time. The y-axis is the number of completed tasks. It indicates that MPSV can complete more tasks under the same time threshold. Okay, let me conclude. We present a symbolic verification method for MPI programs. The basic idea is to combine symbolic execution and model checking in a synergy manner. MPSV supports the verification of long-blocking MPI programs. The evaluation indicates the promising of MPSV. MPSV is free and open source. Please visit this website for more information. Thank you for your attention. This ends my talk.